Hi. First off, I'd like to thank the organizers for arranging this conference. It's been very interesting. And thank you all for being here to listen. So this is going to be joint work with Zhang, and also it's very much based off the previous talk. So it's kind of nice to see these back to back. So just to give an overview of what we're going to talk about, we'll start with kind of a background on optimal transport, which will have a lot of overlap with the previous talk. And then we'll talk a little bit about Hessian manifolds and how our results fit in and kind of what they are. And finally, we'll give an application to this, which is, making money. So this might be an interesting application. Okay, so optimal transport is this kind of ancient field, goes back to, I think, 1781. And the problem is kind of you want to move from one configuration to another. So in French, there's this wonderful word for the raw material that you need to move, which is déblat, which doesn't have an English equivalent. So you take this raw material and you move it to the place in the construction site, the remblai, where it will be used. So you take a configuration mu and you move it to nu. And Gaspard Monge was originally thinking about moving literally piles of sand around a construction site. He assumed that the cost of doing so was basically the product of the mass and the distance. But this is not the most commonly used cost function that we use now. So nowadays, what we generally use, or the most common cost, is that you take the distance between 2 points and you square that. And that's called the 2 Wasserstein cost, and the p Wasserstein cost is when you raise it to the pth power. Okay, so to formalize this problem, what we're going to do is we're going to want to use the notion of a coupling. So what we do is that we take x and y as probability spaces, and then we put a measure on their product so that the marginals of x is our original measure and the marginal on the y is our target measure. And then we denote the space of all couplings. So here's some pictures of some couplings. So there's kind of 2 extremes of coupling. So the trivial one, which I don't have a picture of, is when gamma is just the product measure on x and y. And in this case, the random variables x and y you can kind of think of as independent. The other extreme is a deterministic coupling, which is when the support of gamma is contained entirely inside a graph. So that's kind of the picture on the right-hand side. Okay, so the Kantorovich problem, the framework for optimal transport, is that we take a cost function, c, and we try to find the optimal coupling, the best way of transporting by minimizing the total integral of c with respect to the coupling. So Monge in his original work considered deterministic couplings. So basically the difference is that for Kantorovich framework, we can split off mass and send it to multiple points. But in Monge's framework, everything at one point gets sent to a single other point. Okay. So in general, you can show that the Kantorovich solution exists for very, very general problems, but there's no guarantee a priori that it's going to be deterministic. So Monge's problem might not have a solution. So we can ask ourselves, when is optimal transport deterministic? And right now I have this theorem, which was originally proved by Bernier in '87 and then generalized to more, Bernier proved it for the 2 Wasserstein cost, and Gangbo and McCann kind of generalized it, which gives some very technical assumptions and then shows that in this case, the optimal transport is actually deterministic. But I'm not going to go through. Let's just focus on the highlights. So if x and y have the same dimension, certain regularity and non-degeneracy conditions hold, then the optimal transport is deterministic. Furthermore, it's actually induced by a solution to a Monge-Ampere equation. So for the two Wasserstein costs, that C exponential is the usual exponential map on a Riemannian manifold, but I'm not going to write out what the C exponential is in this talk. It's in the paper, but it's not really important. It's just the thing to keep in mind is that this thing should look like a Monge-Ampere equation. Okay, so once we have deterministic optimal transport, we can ask, how regular is this thing? Do bits that started off nearby end up nearby, or does it kind of break apart and send it to very, very different parts? So in view of the previous theorem, basically from a technical standpoint, what we need to do is to prove an a priori C2 estimate on this thing. That's the technical way of saying this is proving continuity. So note, first off, that we're not going to be able to do this unless we make some convexity assumptions on the support of mu and nu. So the above example is kind of due to Caffarelli. And what you're doing is that you just consider the measure, which is the uniform measure on the two sets I've drawn. So you transport from x to y. And in this case, the cost function is the two Wasserstein costs, so it's distance squared. And it turns out that for these two sets, the black segments are singular sets. And by that I mean the solution to the Monge-Ampere equation, this kind of potential function, has corners along these black segments. So we know we need to make some sort of convexity assumptions. What's going on is that y is not convex, and that's kind of the issue. Okay, so for more general cost functions, the breakthrough work was done by Ma, Trudinger, and Wang, who proved regularity under the assumption that a certain fourth order quantity is positive definite. So in this talk, I'm going to use a stronger version of their theorem, which only needs non-negative definite, which was proven later by Trudinger and Wang. So here's the start of the theorem. Then it goes to the next page. And then we get our conclusion. So I'll come back to this at the end, hopefully, but we're going to focus on this. And I'm going to use this notation throughout the talk, that if I have C sub ij, that's for these capital I's and J's are multi-indices. That means that I'm taking the partial derivative with x before the comma and the partial derivative of y after the comma. So Cijrs is two derivatives with respect to x, xi and xj, and then two derivatives with respect to y, yr and ys. And furthermore, when I raise a Cij to a superscript, that's taking the matrix inverse. So this is a closed form expression for the Ma-Trudinger-Wang tensor, the MTW tensor, which was mentioned previously in the talk before, but this is actually the closed form of it. So the key condition that we need to consider is when this thing is non-negative definite. That's kind of the important. So a cos C is said to satisfy this condition if we assume that C and eta are orthogonal to each other, and we have basically something like non-negative definite or even positive definiteness for this tensor. Okay, so let's just review some properties of this that we can kind of see first off. So first off, it's fourth order, right? There's four derivatives. It's nonlinear in C. It is very complicated. It's actually non-local, and what I mean by that is that it depends both on x and on y. You can't kind of figure out what it is solely from knowing it in the neighborhood of x, which makes it really, really difficult to study this thing. So it's actually tensorial so long as we interpret eta as actually being a covector instead of being a vectors. The origin of this is that Schrödinger and Wang are experts in PDEs. So they understood the orthogonality, but from a differential geometric point of view, it's better to think of it this way, at least when written like this. So for the two Wasserstein costs on a Riemannian manifold, Loper showed that it's actually 2/3 of the sectional curvature on the if you restrict to the diagonal where x equals y. So what this shows is that it's really hard to find MTW non-negative costs. For instance, MTW non-negativity implies that the sectional curvature is non-negative, which is a very strong condition. So as a result, most natural cost functions don't satisfy this condition at all. Okay, so as mentioned in the previous talk, and I won't go over this, Kim and McCann introduced a pseudo-Riemannian geometry for optimal transport and understand the MTW tensor really well. MTW non-negativity is in some sense necessary for regularity of optimal transport, in that if it fails, you can find smooth measures where the regularity fails. And finally, I'll just mention a very deep theorem of Figoli, Rifford, and Voani, which is that if you take a round sphere and you slightly perturb it, then the two Wasserstein cost still satisfies MTW kappa, which is a very difficult theorem. Okay, so that's our brief recap of optimal transport. I'm going to take a detour in Hessian geometry, and then we'll come back and kind of tie these two things together. Okay, so I'll recall that there's kind of two definitions which are equivalent for a Hessian manifold. The first is that it admits two flat connections, which are conjugate to each other. And that's kind of the information geometric way of thinking of it. And then the differential geometric way of thinking about it is to consider it as an affine manifold, and that in each, and that you can find an atlas of coordinate charts which are affine, and so that in each coordinate chart there's a convex potential such that G is given by the second derivative of this potential. So these are equivalent, but we're going to need to use both perspectives here, so it's helpful to know both. So given a Riemannian manifold with an affine connection D, we can consider its tangent bundle and put an almost Hermitian structure here. And this is kind of a classic construction known as the Sasaki metric. To give a very brief overview of how this works, basically you use the connection to induce a vertical and horizontal decomposition of the tangent space. The vertical one is actually just given by the kernel of the projection map, so it doesn't depend on the connection, but the horizontal space is defined in terms of the connection. So using this decomposition, then we can kind of write the almost Hermitian structure as the only thing it could be. You put G on both the horizontal and vertical space, and you put J to be the only thing it kind of could be. So once again, this is probably not enough information. Our paper has more details on this. So we can ask ourselves, when is this thing going to be a Kähler manifold? If you have almost Hermitian, the next thing to ask is, when is this thing nice? And it turns out that it's a classical result of Dombrowski that this construction is Kähler if and only if M were Hessian to begin with. So this is kind of the motivation for considering Hessian manifolds. So in the case when this is Hessian, we can compute its curvature. And we find the following expression for the curvature of the tangent bundle of the Sasaki metric. So I'll note that this is negative what Shima defined to be the Hessian curvature. So this thing right here is negative the Hessian curvature, which is kind of a common thing in Hessian geometry. So the hope is that this hopefully looks familiar, and there's some relation here, right? Like this thing and, well, ignoring these terms, looks like it should have some relation. Okay. So what we're going to need to do to make this relation between optimal transport and the curvature of the Sasaki metric precise is to consider a special class of cost functions. So so we're going to consider cost functions of the form C of x minus y for a convex function. And then here, what's going to happen is that M must contain the set x minus y, defined like so. So just so that everything is well defined. On M, we're then going to give it the Riemannian metric defined by C as a potential, kind of the natural thing to do. And then we're going to consider the Taylor-Sasaki metric on Tm and its curvature. Doing so, we get the following theorem, which is basically that the MTW tensor is 2 times the difference between two sectional curvatures. So we're calling this the anti-bisectional curvature because it's basically a bisectional curvature, except that bisectional curvature has a plus, whereas this has a minus. And I have these sharps here because we should really think of eta as being a covector, not a vector. So to make this precise, it's better to put sharps. But that's just a technical detail. The key thing to keep in mind is that MTW tensor and the curvature of this Sasaki metric are deeply related. Okay, so this is all well and good, but what can we do with this? So the kind of the first application, and this was inspired by work of Pao and Wang, is to consider some stock options. So we have various stocks that we can buy, and we want to find a strategy of buying stocks which outperforms the market in the long run. So what we're going to assume is that the market weights follow some unknown, discrete, deterministic process. So we don't know what the process is, but we assume that it's kind of set out. And there's 2 technical assumptions which I'm not including here. And then a portfolio function is something that takes a current state of the market and tells you what your investment strategy should be. Okay. So as I said, we want to find functions which outperform the market portfolio, which is where we just buy and hold on to our stocks indefinitely, almost surely in the long run. And these are called pseudo-arbitrages. So Pao and Wang showed that pseudo-arbitrages are induced by the solutions to optimal transport problems for the following cost. This looks a lot different than the C alpha costs from before. And I haven't included the alpha, but this is actually equivalent to the C alpha cost, or I guess it's the C1 cost after reparameterization. So with these optimal transport problems, you can often reparameterize them and get equivalent costs. This is an equivalent way of writing the costs from the previous talk. So here, xi's are the logs of the pi over pn, with pi the market weights. Okay, so given 2 probability distributions with some regularity assumptions, we can find a pseudo-arbitrage which transports one measure to the other, and we want to figure out a regularity theory for these. More concretely, we want to know that if the market changes this a little bit, that we don't all of a sudden sell off like all of our stock in one option. That basically our investments depend continuously in the conditions. So as I said, here's the cost function. It turns out that those last 2 terms don't affect the optimal transport at all in some technical sense. So it's equivalent to consider the following cost function, which is now a cost function which is now a C cost, basically. Okay, so now we can kind of go back and revisit our Mautrer-Dinger-Wang theorem and try to use this to get regularity for that cost. Okay, so as I said, first things first, let's consider the MTW tensor. So we're going to consider Rn, take its tangent bundle, and on the Rn put the following Hessian metric. This should look familiar if you're familiar with Hessian geometry, because it's the kind of simplest example of, or really maybe the only example of something with constant, I guess in that convention, negative Hessian curvature. So in the complex geometric language, this has constant positive holomorphic sectional curvature, which implies that its MTW tensor, corresponding MTW tensor vanishes. And I'm not going to go into so much detail because this was mentioned in the previous talk. This is an equivalent way of writing the result that the MTW tensor vanishes. Just as to give some geometric intuition for what the Hessian manifold actually looks like, it's the round metric on the positive octant or orthant of the sphere. It's not complete. It's bounded, and you can't complete it to a metric on TSN minus 1 because spheres are not affine manifolds. So there's really some kind of non-completeness built into this space. And it turns out that as a complex manifold, it's locally holomorphically isometric to CPN minus 1, but it's maybe not so easy to see that isomorphism. Okay, so let's revisit our other assumptions. So the first two are kind of smoothness and non-degeneracy assumptions, so those are maybe a bit more straightforward. But we have this relative C convexity assumption about the supports. And if we think back to the Caffarelli example, this is giving us our convexity assumptions that rule out his example that we saw earlier. So it turns out, and it's a proposition, not so hard to prove, is that a set Y is relatively C-convex with respect to X if for any X and little x and X, the set X minus Y is geodesically convex with respect to the dual connection, not the primal connection that we use to make the Sasaki metric, but the dual connection D prime. So just to bring it home to this problem, the one that we're actually working with, in this case, there's a correspondence between the x coordinates, which are the natural parameters of the multinomial distribution, and the market weights p sub I, which are the sufficient statistics. So as a result, a subset Y is relatively C-convex if and only if it's convex as a subset of the probability simplex in the usual sense. So for this example, relative C-convexity is actually much, much simpler. This is something very special about this cost function. It's just that it's convex in the usual sense. Okay, so we can put this all together and basically obtain a regular, and use the Matsuyama-Wang result and get the following regularity theorem for the costs that Powell and Wang considered. And you can also use this to prove regularity of the displacement interpolation, which was a question that they had asked in one of the papers and kind of was the inspiration for this entire line of work in the first place. So heuristically, what does this mean? It means that small changes in the market induce small changes in the investment strategy, which is good. As a disclaimer, use this strategy at your own risk. I am not using this personally, and it only works almost surely in the long run. So you can lose money in the short term. There's no guarantees, even theoretically. So I'd like to finish with just a few open questions that we've kind of been considering. So the question is, can we understand, classify convex functions which induce some sort of positivity of the curvature on the tangent bundle. So we've kind of been thinking about this. The next thing is that the Mautrer-Dinger-Wang result is some very deep theorem involving Montan-Perry equations. And it'd be interesting to know if there's some way of proving this in terms of complex Montan-Perry equations, now that we have a complex formulation. And finally, it'd be interesting to know if there's other applications for these sorts of cost functions. We have one, but we'd like to know of others. So I'd like to thank you for your attention and for being here.
I have a question, but it's question to Junza. So, are there any relation between the MWT tensor and peak invariant in affine differential geometry?
Peak, you have three derivatives and three derivatives.
Yeah.
This is four.
Four. So anyway, so I have a comment. So in so Hessian case, induced equivalent volume form satisfies Montan-Perry equation. So I think your result is related to the affine differential geometry also in this framework. So
You mean in the Hessian case?
yeah, Hessian case. Induced equivalent volume form satisfies Montan-Perry equation.
Yes, yeah.
So I think B the analysis school
Yeah.
Result is related to in this framework.
Yes. So for the Hessian, the volume form is the determinant of G related to the alpha.
Yeah, so that's, I believe that's a somewhat different Montan-Perry equation. Because we have looked at that in unrelated work to this. But that Montan-Perry equation and the Montan-Perry type equation in the beginning here, Montan-Perry just means that you're something like the determinant of the second derivative, but you can have many other terms. The optimal transport Montan-Perry equation is different from the kind of the Montan-Perry equation involved with volume forms, right? That's more of a standard like log det of nebula squared u is equal to some constant or some constant times u, or that's the one involved for the equiaffine. Yeah. Montan-Perry equations are kind of a broad class of equations. The last slide?
Yeah, do that.
Okay. Sorry, I have too many slides.
Open, please. Yeah, the second one.
Yeah.
Do you have a partial result?
No, we don't know anything. So the one, so the pseudo-Riemannian theory is in some sense better. I'm a complex geometer by background, so kind of the things that I'm thinking about this is nice from a complex geometry point of view because we can make nice examples and kind of understand the theory. But the pseudo-Riemannian geometry of optimal transport has kind of some advantages right now, which is that A, you can deal with any costs, and B, there's this beautiful theorem of, I think it's Kim, McCann, and Warren, which basically shows that there's this very nice understanding of the graph of the optimal transport as some sort of like minimal surface after conformal change of the pseudo-Riemannian metric. And we'd very much like to have something like that to some complex understanding of the associated graph here. but that's currently an open question. So I know what, I don't have any partial results, but I know kind of what I'm looking for because it should mirror the case for the pseudo-Riemannian theory.
No, regarding the first question, you have to classify something.
For this question. We have,
Evaluation.
yeah, so we have some partial results we're kind of working on. So basically what you do is the name of the game will be something like you assume some strong symmetry and some strong curvature properties, and then you get that you were the two Wasserstein cost all along. There's these kind of gap theorems in Kähler geometry, which show that under suitable positivity assumptions that you have to be flat, you have to just be Cn. And there's a Yao's uniformization conjecture is kind of the most famous example of this because it says that if you have positive bisectional curvature and you're a complete Kähler manifold, that you're just holomorphically, you're just holomorphic to Cn. And this has been partially proven, but the moral of the story is that we should hopefully expect something like this, which to show rigidity of cost functions which have this property, and correspondingly convex functions which have this non-negativity curvature properties.
You have comment? Thank you very much.
Thanks.